lot of the research that I'm presenting in this work. So I will give some time for questions towards the end of this talk, so feel free to ask any questions at that time. And you'd also find here our website and my email, where you can also correspond with me directly afterwards as well. As a broad overview, the research in my lab consists really on taking scientific discoveries in the lab towards nanotechnology applications. In this regard, we do conduct a lot of research on nanomaterial synthesis, characterization, defects, functionality. Then we use these nanomaterials for nanoelectronics. We make thin film devices, transistor devices, sensor devices, energy devices, and so on and so forth. And in some cases, we observe phenomena that requires a call to deeper scientific research in terms of trying to understanding the underlying physics of phenomena. So from time to time, we get into material physics, device physics, to elucidate phenomena that we're observing. And indeed, the focus of this talk today on defects is based on a phenomena that we first observed, which are memristor effect in 2D materials. And that led us to question what is the underlying physics of the memristor effect in 2D materials. And then that led us really to the role of defects in these materials. Let me start off motivating this talk by just briefly describing the history of electronic devices. So over the last 100 years or more, a single device or so has been the main driver for electronic technology. 100 years ago, it was vacuum tubes, and then we saw the era of the solid state begin around 1960, with diodes being the first main solid state device. Transistors then took over and dominated for a long time, and more recently, memory devices have been the dominant driving technology or device for electronic technology. Memory devices are actually, some would argue much richer in terms of material science and physics. For example, you could have semiconductors used in transistor configuration as flash memory based on charge trapping phenomena. You could have ferroelectric memory based on spin modality. You could have materials that change phase from crystalline to amorphous, and then that leads to so-called phase change memory. And you could have solid electrolytes, which is ionic transport in materials, and that's so-called CB-RAM, and a variety of metal oxides lead to resistance change memory. So the latter two or three are colloquially called memristors, and this is really similar to the effect that I'll describe, which is what we observe in atomically thin materials. Let me use this one slide to explain the basic phenomena of memristors in, let's say, for example, in metal oxides. It's really an application of defect. Often we want perfect materials, but for memory effect, in this memristors, some defects are needed, and this is really exploiting this defect. So if you make a two-terminal device with a metal as a top and bottom electrode, and then you have a non-conductor like an insulator or dielectric as the active layer, even though there may be some limited amount of defects, when you measure the current across this material, the vertical current versus voltage is going to be close to zero. So we say this is the off state. I like to think as the memory switching very similar in analogy to the lightning effect. So in the case of lightning, you consider the sky as a top electrode, the earth as the bottom electrode, and the atmosphere as the insulator. And so on the application of a very high electric field, such as lightning, you get ionization of the atmosphere, and so you get current flowing from the sky to the earth. This is very similar to what we see in at the nanoscale in solid materials. Uh, when you apply a high electric field, you can ionize the dielectric or insulator, and in its wake, you leave behind a conductive path or filament. So that leads to high current flowing. So this is what is known as the on state or the low resistance state. And the wonderful thing about this is you can cycle this set and reset many times. In some of the most advanced materials, you can cycle this billions of times. So just like transistor scaling, memory, non-volatile or so-called RAM or emergent memory or memristor scaling has attracted attention over the last decade or more. And for the same benefits as you have dimensional scaling in transistors, you also have benefits related to dimensional scaling, especially in metal, insulator metal type memory devices. So that includes three-dimensional density. You can stack them in 3D layers. Also in two-dimensional, the pitch can be made shorter in 2 dimensions. Many especially metal oxide type devices become forming free when you go to thinner structures. It's certainly going to consume lower energy because you have to move matter over a shorter length scale. And for the same reason as length scale, you can achieve faster switching time. However, just like as in transistors, there are inevitable problems that come with dimensional scaling. Likewise, in many or most metal oxide type RAM and similar devices, there are issues that come with dimensional scaling. And that includes higher leakage. Please keep in mind that higher leakage then means that you have lower on-off ratio, which often translates to lower or reduced reliability. And the fundamental reasons for these issues are because most conventional emergent memory, like metal oxides, are disordered materials. So you have a lot of pinholes when you go to very small thicknesses, and then these pinholes begin to create a direct short between the top and bottom electrodes, and so the phenomena begins to fade out. So I began to consider this a couple of years ago, and it dawned on me that maybe two-dimensional materials could rescue this problem. Just like two-dimensional materials are proving to be useful in solving some of the dimensional scaling problems in transistor devices, uh, I thought they may also help address this issue of leakage currents in emergent memory. So, of course, many of you are aware of two-dimensional materials. The graphene is the most popular from the graphite system. You have HBN, which is a pure insulator, and you have MOS2 and similar semiconductor materials. So what is different about these two-dimensional materials for memory applications compared to, let's say, oxides or chalcogenides is because these two-dimensional materials are crystalline materials. So issues related to leakage because of disorder are not going to be present in these two-dimensional films if they were used as the active layer in a memory device. And so with a 2D platform, you could select the metals from, let's say, graphene or similar materials. You have semiconductors like MOS2 or TMDs, and you have dielectrics like HBN, which can both serve as the active layer. So the 2D platform is you could get, let's say, the entire cell to be less than a nanometer or 2 nanometers. So it's an excellent platform for precision defect engineering. You can control the amount of defects through a variety of means, and it's very, very scalable. So this scalability leads to certain performance advantages, which includes very high densities that can satisfy both computing and storage applications. It's smarter, which means it consumes much less energy, approaching the thermodynamic limit. I'll show an example of that towards the end. And it can be much faster in terms of switching time because the length scales are at the very ultimate limit of material thickness. However, when we first began working on this, there was no report using atomically thin two-dimensional material as the active layer in a metal insulator metal memory device. So we began to consider what kind of structures would make sense. Our early analysis of the literature show that there was no work present. If you look in that year of maybe 2016, there's a lot of papers. Let's say we focus on MOS2 as a prototypical active two-dimensional layer. You see a lot of the paper publications were on material synthesis, applications focused mostly on transistors and sensors. And there was just only one monolayer memory paper, and that was a planar device by my distinguished colleague, Mark Herson from Northwestern University. Of course, the planar devices have their own advantages. However, they're not really able to afford the kind of densities that one gets with the vertical devices. So we said, okay, let's consider making these vertical devices using gold as an electrode, which rules out gold being a noble metal, rules out metal oxides and may form at the interfaces that could compete for the phenomena. So we chose gold. Subsequent metals have now been used also in these kinds of devices. So my first student working on memory, then we didn't know if this was going to work, to be quite frank. But within 6 months of making prototypical devices, she was actually able to get working results for the first time using this monolayer two-dimensional materials as the active layer in memory. So you see the cross-sectional TEM here. We call this atom ristors, which is just a technical jargon to denote memristor effect in atomically thin materials. So you see here a typical bipolar memory curve that we observe. Initially, the current is very, very low, so we call that the high resistance state following standard terminology. And then around 1 volt in this particular sample, you get an abrupt switching to very high current. So then that is the low resistance state. And you can return to the original state or reset the device by applying the opposite polarity of voltage. So that is known as a bipolar memory effect. It's a non-volatile phenomena. So if the memory state is in the high resistance state, which is this blue curve, it's going to stay there. In this particular case, this is about a week long. We've now done measurements that are months long. So we can say it stays there more or less as a non-volatile resistance state almost indefinitely. So initially, when we got these results, there was a lot of technical concern that this phenomena may not be intrinsic to the two-dimensional material because it has not been previously observed. So following the advice of several colleagues, we decided to check not only the materials that we were growing, but we checked in similar MIM devices using MOS2 materials grown by the best groups in the world, using CVD, MOCVD, different precursors grown on different substrates, different number of layers, and even exfoliated samples. And we could conclude that indeed this phenomena, memory effect, is intrinsic to this atomically thin two-dimensional materials. Since then, we've now done increasingly exhaustive studies, not just on MOS2, but on a growing library of 2D materials. You see here, we've done studies on the metal sulfides, the metal selenides, and heterostructures of two-dimensional material, tellurides. And indeed, we've also studied the thinnest 2D insulator, which is HBN, and that also shows very, very promising memristor or resistive switching phenomena. The detailed characteristics of all of these materials are still ongoing, and it's at this moment difficult to draw a conclusive trend because there's a lot of variability as there is with any new emerging device. There's a lot of variability, so it's difficult still to correlate the properties of the switching with the different materials. We have conducted a variety of performance measurements on these samples. This is very important for device applications and may appeal to some of you interested in the engineering and device properties of this memory devices. So one important performance parameter is the so-called endurance. This is the number of times you can cycle this effect from off to on, off to on, and off to on. Typically, this is done by pulse testing, but when we started this work, we hadn't developed the capability, so we did DC endurance testing, which is a much more harsher form of testing. Nonetheless, we can get in some current samples now hundreds of cycles, still a long way from millions of cycles that will be the minimum requirement for many applications. So a lot of research still ongoing, but still this limited data indicates that this phenomena can be cycled, and we now need to understand the ultimate limit of cyclability or endurance. Retention, I showed this earlier. Now, whether it's in the high resistance off state or the low resistance on state, the device can persist in that state. Now, this data is for a week long, but our most recent data, the retention is months long, actually. We don't know what the limit is. Of course, because the 2D materials are inherently ultra thin, they're very flexible, so you can place them on a variety of flexible substrates. Shown here device data of the memristor device placed on Kapton or polyamide, and this is the so-called bending endurance. We can bend it repeatedly, in this case over about 1,000 cycles, and the state remains in its initial state. So very, very robust bendability. And if you look at the IV data before and after 1,000 cycles, it's fairly similar to the initial data. So that's very important for example, for wearable applications that you may want to have on-board wearable memory to store data you're collecting from the wearable subject. And very recently, with collaborators in Israel, Professor Elam Yalom's group, we've been able to get very, very precise measurements of the switching time and switching energy. In a nutshell, this phenomena can be switched in less than a nanosecond and consumes really very, very low energy, less than 100 picojoules. In fact, there may be opportunity to drive this energy down significantly, and I'll show later that we can now approach femtojoules and attojoules in some of the more optimized devices for computing. So one of the fundamental questions, especially when you observe new phenomena, is what is the underlying physics? So we, given the debate surrounding our initial results, we spent quite a bit of time trying to understand the underlying physics. So if you look in the older literature, which remains popular today, the work of John Simmons has been quoted and cited for modeling phenomena between metal, insulator metal. So this is actually a picture from the paper by John Simmons talking about insulating films between metal electrodes. And so if you apply this, so John Simmons developed this so-called semi-classical WKB theory that describes electron flow across this kind of insulating barrier between metallic electrodes. And so if you apply this theory to model current flow in our device structures, you see that you don't get consistent results. A lot of researchers believe that the leakage current, even in such crystalline thin materials, the leakage current will still be very high, the tunneling leakage current. But in fact, we're getting very, very, very low tunneling current. So what is the reason? The reason is this theory, this semi-classical WKB theory, completely breaks down for barriers less than 1 nanometer. So John Simmons, in fact, mentioned this in his original article, saying the theory that he was developing in this paper in 1963 assumes insulating barriers greater than 1 nanometer. And the reason is when you go to barriers thinner than 1 nanometer, image force corrections are very much important and cannot be neglected, which is the case for thicker barriers. The other reason this theory does not adequately describe the tunneling current that we've observed is, and this was not appreciated in the original paper by John Simmons, is that this theory assumes you have more or less intimate interfaces. So we can say these are more or less epitaxial interfaces between metal and insulator. But in fact, in the 2D materials, these are not epitaxial nor intimate interfaces. What we actually have van der Waals gap between the electrodes and the active layer. So you have both the van der Waals gap represents tunnel barrier, and then the material represents a tunnel barrier for electrons that want to travel vertically. So altogether, if you take into account this more realistic scenario, then one can accurately account for the tunneling current that leads to the off state in this material. So what about the mechanism for switching in the on state? So we hypothesize that defects in the two-dimensional material may be responsible for the switching. So we began to look at the variety of defects present. The most abundant defect is a single sulfur vacancy given here by the energetic formation energy calculations. And the second most abundant is the double sulfur vacancy. So you have the sulfur on top and the sulfur below the molybdenum or metal atom missing. So we said, okay, this might be responsible, and perhaps we can use scanning tunneling microscopy, STM, to further elucidate how this defects might be playing a role. So we decided to use STM, which I believe for this monolayers is really the best tool to evaluate the science and the mechanism of switching. And this experiment is conducted by my postdoctoral scholar, Dr. Sivan Haas. And the idea is to use STM in the three modalities that STM affords. You can use STM, of course, for imaging. So here you see a clean area of the MOS2, and here you see areas that have defects. These defects in particular are single or disulfur vacancies in these white circles. And then you can also use the STM in transport in contact mode. And so if you look at, for example, if you do transport in this clean area, you see, more or less an ordinary IV curve that represents diode-like behavior. Nothing unusual about this. However, if you do STM in this local defective regions that contain these vacancies, you clearly see now hysteresis, which shows the emergence of this non-volatile memory effect. So we could conclude that defects are playing a role. However, that's not the full picture. So I challenged my postdoc, Sivan Haas, to see whether we can actually do imaging and transport sequentially before and after switching. And so this is what this experiment on this slide revealed. So here we have the atomic structure of the MOS2. In this particular case, we're focusing on the disulfur vacancies, which is imaged here in the real sample. And then the idea is now let's do transport to switch the resistance to the lower state. So you see now it's been switched to the red curve, which is the low resistance state. The hypothesis then is that a metal ion from the electrode, in this particular case, will be the STM tip is emulating the top electrode. The metal ion will come and get absorbed into this vacancy. If that hypothesis is true, then we should be able to see in the subsequent STM image the evidence of this. And this is in fact what is shown here in this STM image. This bright spot here, further analysis indicate that this is most likely a gold ion. The dimensions are consistent with what one would expect of a gold ion, which is what the STM tip in this experiment are made of. So then this is for the set process. What about the reset? So we said, okay, using the STM to apply the negative polarity voltage, one should be able to desorb this metal ion. And that is, in fact, what is illustrated schematically here. And you see the reset curves shown here. These are the STM transport measurements. And then subsequent imaging confirmed that we can return to the initial state of the sulfur vacancy, in this case, the disulfur vacancy. So yeah, these experiments conclusively point to a virtual conductive point mechanism, which I'll illustrate in this slide, and perhaps this is one of the most important slides of this presentation. So we have a metal electrode. We have a crystalline sulfur MOS2 layer with discrete sulfur vacancies. In this example, I'm showing a single sulfur vacancy. Of course, this material, when you do the MIM IV curves, there's no current flowing or very little, so it's in the off state. And when you do STS spectroscopy with the STM setup, you see that clearly this is an insulating film. Either whether you have a pristine MOS2 layer, which is a blue curve, or even in the presence of a single sulfur vacancy or disulfur vacancy, it's still an insulating state. So the vacancy state itself is not conductive. Now, as you apply the high field due to electrochemistry, you have this metal ion then absorbed into this vacancy. Then the IV curve shows a conductive state. And then when you do the STS, which is a measure of, let's say, the density of states, you see that you have a finite density of states that reveal that this is now a conducting point. That local point is now conductive. So we call this the virtual conductive point mechanism, which is slightly different from the physical conductive point mechanism in some other emergent memory. And this difference is illustrated here. Here you have the conductive bridge mechanism known in some electrochemical memory cells, where you have a physical connection between the top electrode and the bottom electrode, and that bridge consists of the metal atoms aligned in this one-dimensional bridge that is often called a filament. That contrasts with this virtual point. In this virtual point, so you have this gold absorbed into these sulfur vacancies, but you don't have a physical connection. But you still maintain a van der Waals interface, so it's not physical. Nonetheless, the material is locally, it has a high density of states, so it's a conductive density of states at this local point. So you have tunneling transport from the top electrode to this conductive state and back and all the way to the bottom electrode. So that is what we mean by virtual. Unlike the conductive bridge, where there's actually a physical connection from top to bottom. So the other contrasting properties of these two classes of memory devices are the conductive bridge devices are disordered materials. The 2D materials, as I mentioned, are crystalline. The conductive bridge are based on filament formation. Here, it's a conducting point creation. Both of them represent one-dimensional transport. The one in particular through the 2D is one-dimensional transport through the band gap. They're both linear IV characteristics. The ohmic is obviously a linear phenomena, but that is also the same for the direct tunneling. It's also a linear phenomena. Both can be used for memory and computing. However, the conductive bridge is not suitable for radio frequency or 5G switches, while the two-dimensional, this conductive point mechanism is very suitable because it can afford the very low resistance needed for those applications. So now let me use maybe a few slides to give you some of the application prospect of this this new phenomena in this material. So I'll just highlight some of the work by other distinguished scholars across the globe. So Feng Miao's group has focused in a few years ago trying to improve the endurance. So these are pulsed endurance data. They show that you can get above 10 million cycles. However, in this particular MOS2, this is still a relatively thick layer, and the way they achieved improved endurance is by slightly oxidizing the MOS2. It's unclear whether this slight oxidation strategy would work for monolayer films, so that requires further research in the monolayer extreme. Samsung has also been very active in this field. They published just 2 years ago. In fact, they were the first group that directly reproduced our work. In this particular case, they decided to focus on 2 layers of MOS2 because the 2-layer stack is more reliable for the memory than the monolayer stack. And they demonstrated the first neuromorphic computing with this 2-layer MOS2 stack. You can see the potentiation and depression representative of the synaptic operations in the brain. Han Wang's group at USC published remarkable results a few years ago where in this particular case, they're looking at boron nitride instead of MOS2, and similarly oxidizing that boron nitride, which is a 3-layer boron nitride stack. They could get incredibly low currents. If you just look at the data here, we're now talking of the picoamps. And very recently, a collaboration we enjoyed very much with Mario Lanza's group, who is now who is now at KAUST in Saudi Arabia. We showed 24 programmable resistance states for neuromorphic computing, demonstrated an artificial neural network, and very importantly, switching energies. Now we're talking about switching energies in the zeta joules. This work here is based on boron nitride. So you can see that there's a lot of opportunity both for neuromorphic computing, artificial neural networks, memory storage, to utilize these 2-dimensional materials for their advantages, including their energy advantages. So I'll use perhaps the last set of my slides to focus on the new application, which are RF or 5G switches to enable 5G networks. 5G networks are very important in today's society and are becoming more and more ubiquitous for many reasons. And I hope this slide gives you an idea of the ecosystem that 5G combined with artificial intelligence enables. You're talking about industries in electronic health, agriculture, transport and goods, education, logistics. All these industries need to connect to the infrastructure, to the network, and they need to do it at low power, at very high data rate to access content and to enable artificial intelligence. So switches that can toggle between all the different bands and toggle even within the same band at different times. These switches are very critical, especially low power switches, because all of these are, in many cases, edge networks, so their power consumption should be very, very low. So a few years ago, as we began to study this phenomenon and look at new applications of this non-volatile switching in 2D materials, it became clear to us then that this is actually very suitable for the radio frequency of 5G switching applications. So in that application, the key requirements are that in the on state, you want very, very low resistance compared to 50 ohms, which is the standard impedance for RF systems. So let's say you want something less than 10 ohms. In the off state, you want the resistance of the switch in the high resistance state to be greater than kilo ohm. Oftentimes, the off state is dominated by the capacitance of the material. So you want the offset capacitance to be femtofarads or less. So just to give you what the current emerging solid state switches look like. So here is a C-off versus R-on. This combination of resistance and capacitance is often known as a figure of merit. The inverse of that is the frequency, so it should be above a terahertz. It's not the operating frequency; it's just a figure of merit to compare devices. So you see the MEMS devices here have very low on capacitance and low off very low off capacitance and low on resistance. And then you see the phase change in transitional metal oxides, a little bit higher for both properties. And then the solid state switches, which are the dominant switches today, the transistor switches, have relatively orders of magnitude high resistance, on resistance, and high off capacitance. So they're limited to single terahertz figures of merit, while the MEMS can go much higher. So what about the 2D material? So I won't bore you with a lot of details. I welcome questions, and you feel free to either ask at the end of this presentation, or certainly you can always inquire by email. These are the standard so-called S parameters. Those of you that do radio frequency measurements will be familiar with this. So you do this kind of S parameter measurements as a function of frequency for the device in the on state and the device in the on state and off state. So what your ideal response is in the on state, 0 dB is lossless. So as close you are to 0 dB is a testament of how good the device is. So we see here on resistance less than 3 ohms is actually very good for this nanoscale submicron device. In the off state, typically for applications, you want this to be as negative as possible. So many applications will say minus 20 dB. It should be better than minus 20 dB, and certainly minus 10 dB even in some applications. So we see up to 70 gigahertz. It's roughly better than minus 30 dB. So the isolation for a single switch is very good. So the figure of merit, this combination of resistance and capacitance, is actually the highest figure of merit, even though this 2D RF switches are much more nascent than the more established candidates I showed in the previous slide. And so this table is actually very timely for me to show right now. You see here that I didn't talk about our HBN switch, but we've also published on this more recently. So we see for whether the HBN or MOS2 switch, we can achieve figures of merit of frequency above 100 terahertz. We're talking about control voltages in the single digits, roughly 1 volt or so. All of this can be integrated on a variety of substrates and under ambient conditions. Switching times are less than nanoseconds, and you can make this these devices in nanoscale form factors. The HBN, the main advantage is the HBN because of this higher band gap and material stability. It can handle more RF power. So we've gone to 20 dBm and in 30 dBm in the on state. So if you compare this with the other emerging candidates that have been studied for much longer, you see that the 2D materials essentially outperforms all these other materials, including MEMS devices, phase change devices, VO2 devices, in almost all respects, all metrics that are listed here on this table. I will now move on to wrap up this presentation with a summary and a highlight of the pressing challenges. With that, I'd like to summarize. So I've only actually shown about 5 materials, 4 TMDs and HBN that feature memory effect, but in fact, as I mentioned, there are hundreds of non-conductive two-dimensional materials, so there's a lot of opportunity for material science, research, and physics. For those in the audience looking for topics, I would highly encourage you to consider exploring many of these materials for memory. They have many advantages compared to emerging devices, and the main challenge now is to get the endurance to be millions or billions of cycles dimensional devices. So first of all, opportunities. There are lots of opportunities. We've just really began to scratch the surface of utilizing defects. So, the main point of this presentation is that defects can be utilized for function in 2D materials. In this case, these are memory functions. But we've not really designed the defect. So there's a lot of opportunity to look at these defects and design them in conjunction with metal ions in order to optimize their energetics. So there are thousands of defect structures available to understand, hundreds of materials. And so this work by collaborators from UPenn point to an opportunity that if we can choose the right set of materials and the right defects in this crystalline 2D layers, we may be able to get the kind of energetics in terms of energy consumption that we seek for a variety of applications. There's also quantum applications of this defect, which we have begun to look at. And so this very nice work by Diakonov and co-authors showed that some of these defects can be spin polarized, and then you can manipulate them as for quantum computing, like qubits. What are the challenges? So yield remains a challenge. Again, these are relatively nascent type devices. So when we first started, our yield was very low. We're talking maybe 10%. My student that graduated this summer, he mentioned in his presentation that yields, can now approach 70, 80%. So the yields have improved, but still, there's still a lot of opportunity to improve the yields further, and that depends on materials growth and transfer. Endurance is the biggest performance challenge today. How can we get the endurance to be millions of cycles, especially as we focus on, let's say, monolayer or bilayer two-dimensional material? So that is an opportunity. If there are students in the audience looking for interesting technical challenges or room opportunities for innovation, I would strongly encourage that you consider some of these challenges. And as I mentioned, energetics are very important. I showed already that in some of these devices, like the HBN devices, memory devices, zettajoules are now possible. How can we systematically design this from the beginning by choosing the right set of electrodes, the right materials, and the right defects to get the kind of performance we want? Altogether, there's actually a big opportunity for 2D materials in memory devices. And so in this review article with co-authors, there's opportunities for 2D materials in 3D integrated, RAM, in phase change memory, in flash memory, as a planar device with ferroelectric layers, planar boundaries. And I've really only focused really on the vertical structure, the so-called memory store or RAM-like structure. So there's actually a lot of opportunity. Again, students in the audience may welcome these other classes of devices for further investigation. So with that, I would like to acknowledge the research staff that have done this work and our distinguished collaborators across the world listed here. And we're very grateful to our sponsors that have allowed us really to push this field forward from the very beginning, where there was only one paper published per year to now where there are hundreds of papers published on 2D memory. I thank you all for your time, and I'll be delighted to welcome and address any questions you might have. These are some of our recent publications that during the pandemic we've been very fruitful. You'll find a lot of details in these publications, but nonetheless, you're also welcome to email me for further discussions as well. Thank you very much. I'll be happy to answer questions at the moment.
So thank you very much for that really, really nice talk. So I can see there's starting to trickle in a few questions in the question and answer, so I can ask one of the first ones that was posted. So it says from, unfortunately, we don't know who the attendee is. A device is like if it be a device is like if it behaves the same expected manner when it's turned off and on. Given the stochastic nature of ionic motion, how reliable is a device to switch to the on state or off state when bias is reversed? Do you expect hysteresis if the electrode atom was not involved in the process and instead we have intrinsic defects moving on the surface?
So my understanding of the question has to do with the cyclability of this phenomena. So the basic phenomena is an interplay between metal ions from the electrode and vacancy states within the 2D material. So the combination thereof then allows you to tune specific performances. We've mostly used gold, but we've also studied copper, silver, and a variety of other metals, and see the same effect of metal ion occupying a vacancy. And then when you apply the reverse voltage, the metal ion can return back to the electrode, and the vacancy state can be retained. So it's actually very repeatable. In the STM studies, Dr. Sivan Haas has observed this several times. Of course, those are very difficult experiments. In device studies, we've observed this hundreds and hundreds of times. So, and others have now begin to observe it in their independent lab and research. So it's actually a very, very repeatable process.
Give people, I guess, a second or two more, I guess, to type the questions, or if someone has a question, wants to raise their hand, we can also do that. See if any attendees.
I see a question from Nikhil.